Hello, Internet. We are live.
Hey everyone, welcome to episode 30 of the Stanford MLSys seminar series. I'm Karan. As always, we have with us Fiodar, Dan, Piero, Matei, and our guest today, Yaron, singer from Robust Intelligence. So Yaron is going to be talking to us today about securing AI systems from operational risk. A little bit about him. So he's the CEO and co-founder of Robust Intelligence and the Gordon McCabe Professor of Computer Science at Harvard. Before that, he was at he started Google and got his PhD from Berkeley. He's received a bunch of awards for his work, too many to list. And he's going to tell us a lot about how we can secure AI systems and what he's actually doing about that at Robust Intelligence. And as always, we're going to have a 30-minute talk by Yaron, followed by a 30-minute podcast-style discussion where you in the live audience can ask questions. You can keep those questions coming during the talk, and we'll keep track of the live chat and try to get those across to Yaron after his talk is over. Yaron, take it away. We're very excited to have you.
Awesome. Thanks, Karan. Thanks for the invitation. Thanks for having me here, and thanks everyone for joining. So today I'll talk about securing AI systems from operational risk. So I'll start by the talk just with something that I think we all know, and basically, and that is that AI is eating the world. And this is a paraphrase about on what Mark Andreessen said back in 2011. If you know, it's like a very famous phrase. Like in 2011, Mark Andreessen said, in short, software is eating the world. And I think kind of in the past several years, we've all become pretty much convinced that not only software is eating the world, but that AI is eating the world. And kind of like just very kind of personally, anecdotally, like something that I've become very much aware of in the past 2 years, kind of like running Robust Intelligence. I've gotten the opportunity to talk to I'd say well over 200 companies. And I think kind of it's pretty overwhelming to kind of see really like how much truth there is in that, like just how much AI is eating up the world, and how basically companies that you'd never expect, right, are becoming so data driven and kind of empowered by AI. So I asked I told our head of product, Daniel, that that I'm giving this talk, and I asked him can you like kind of put together, Daniel, you went to business school, I didn't. You can probably put together some like really great like figure and graph and chart that's really going to like explain to people that AI is eating the world. So this is what he came up with. So and I think that's probably better than anything that I could have imagined. So the lesson is go to business school. But yeah, so AI is eating the world, and we're all happy about that. But some of us are kind of feeling some of the challenges and the pain, and that's kind of what I want to talk about today. So basically, the problem, with I'd say kind of all the companies that I talk to, is that while they are adopting AI technologies and the world is becoming very much data driven, what they're experiencing is a lot of operational risk. So basically, they find that they inherited, with all the capabilities that AI is bringing, they just inherited a bunch of operational risk. So what is it? What kind of operational risk, right? So they have things like kind of bugs in model serving, they have unexpected model behavior, broken data pipelines, distributional drift, adversarial inputs, bias predictions. They have subsets of these, right? And now they need to sort of like figure out, right, how to deal with this operational risk. And this operational risk, normally with the companies that we talk to, there are problems across various layers. But one of the layers is this, it manifests itself in something that we call silent errors. So these silent errors are basically when the model's making predictions, but these predictions are just completely flat out wrong, right? And they go unnoticed, right? And this can essentially lead to catastrophic errors when you're making critical decisions. So let me just kind of quickly start with just some examples of these types of errors. All the examples that I will show are actually examples that we've seen from real customers. This is not going to be on real data for the most part, but all these things we'll see examples that actually happen. So this is on a data set for a model that's trying to predict basically loans, right? And this is a data set, that when you kind of feed that to the model, you get a prediction score of 0.699. But in this case, actually kind of an event that happened was instead of having the right age, somebody instead put in the year that they were born in, right? And instead of the, like age 36, they put in 1985. Okay. What that does to the model is that it then leads to like just a terrible change in the prediction from 0.699 to 0.212. Okay. The issue is that from kind of a system perspective, there is no problem here, right? Data is coming in, the model is producing a number, right? And everything, supposedly makes sense. But obviously, when we look at this, we know that nobody is, 1985 years old, right? We see that there's a problem. A different example that we've seen is one where basically models that highly depend on a certain feature, once that feature is not collected for whatever reason, that highly affects the prediction of the model. So here, for example, like years of education, if that's no longer collected, then that again like affects the prediction of the model quite dramatically, right? And not with not with a good cause. Other issues that we see issues with biases in models. So in this case, you take this is a standard CAD-BOOST model. You would change the here, if you change the race from white to this category that lives in the training data set, you would see like this big change in prediction, even though everything else stayed the same. So these aspects they're not unique only to tabular models. We see this you see this a lot in an NLP model. So in this case, this is from entity resolution task. You have a customer changes like an ampersand sign to an and sign, completely changes prediction of the model. Or some kind of like obvious abbreviations like changing technology to tech all of a sudden erases kind of capabilities of the model. This is in this case, like there's a customer that they're looking at infringement of kind of patent infringement and logos, right? So they have an image model, and what they see is that some actors, what they do is they adversarially kind of like just change the angle of the image, right, so that you can no longer tell that there's like a logo of that company that's being used, right? So these are all issues that are happening kind of that are happening out there, right? And the issue is that, like, again, in all cases, kind of the system, from kind of as a software system, it works well, right? But when we look at it from the perspective of the machine learning system and the machine learning model, right, it just sort of completely fails. All right. So if I kind of try to think about my experience as I've been kind of witnessing this AI revolution from I guess it started from the time that I was Google through the time that I was at Harvard and now, then I think kind of when I sort of look back in 2015 and I think about what was the kind of like the major pain for the majority of organizations, like the majority of the pain came from actually kind of developing AI, right? So and if you think about like 2015, this is before we had open source packages like TensorFlow or scikit-learn, right? We would actually code SVMs, right, in C, right? That's like actually what we did. Now, when I tell that to people here in the company, they sort of, they laugh at me, of course, but that's what we did. So, given that like, kind of, the expertise and developing machine learning algorithms has been limited, a big pain of back in 2015 was actually developing models, right? A smaller set of organizations had the luxury of kind of like being able to solve model development and then focus more on kind of operationals, like kind of things about making the platforms be more efficient, scalable, and things like that. And a small majority of organizations had the luxury of also being, the luxury or the burden of being concerned with AI risk. A lot of times these are kind of companies that were dealing with payments, insurance, things like that. And I think kind of in 2017, right, there have been a lot of open source packages, and we've been moving, kind of solving more and more like AI development, moving more into kind of like AI ops and AI risk group. I think kind of in 2019, there have been a lot of automated tools that have been introduced, a lot of companies that have been doing a great job of that. And also kind of really a lot of great open source tools like TensorFlow, Scikit-learn, all these things that have been coming kind of like mature, and people have been kind of using them quite effectively. And then the problem transitions, I think, from developing AI to more about like developing AI ops and kind of building scalable systems, processing data, things like that. And then kind of, if I look today, then I think that like AI development problem is kind of getting more and more solved. AI ops is a big thing. You know, you want to enable doing these, running this technology at scale, but also AI risk, right, is becoming a major issue, right, as kind of these problems get solved. I think kind of when I look, you know, what's ahead, right, if I think about, you know, 4 years ahead, I feel like AI development is just not going to be an issue anymore, right? I think these things are going to be pretty much standardized. We are still going to be dealing with a lot of AI ops challenges, right? With scalability, distributed computing, and again, there are a lot of really kind of great solutions out there that are solving this problem. And I think that's going to, you know, allow us to focus more and more on AI risk, which is becoming kind of like one of the biggest pains that we have with running AI. So I think kind of in a nutshell, our paradigm in the company is a very simple one, okay? And I can just kind of, I can reduce it to 2 sentences. Basically, the kind of like the first axiom that we have is that basically all these model vulnerabilities, whether it's like bias, bad input, distributional drift, adversarial attacks, all these, they're not separate problems. They're actually, and they're not a problem. All of them are actually symptoms of the problem, and the real problem is AI risk. And once we think about it in those terms, once we think about them all as being kind of like part of, you know, symptoms of the same problem, then the real issue that we need to address is this issue of AI risk. And for that, our second axiom is pretty much that every aspect of AI risk can be eliminated through an appropriately designed test. Okay, sounds very simple, right? And it is, right? So what are these tests? These tests are kind of like, you know, I think there's a lot of emphasis on appropriately designed. So these are tests that are sophisticated in that they are, they're well designed using kind of like the data and the model, and then what they can do is they can basically test, you know, a data set or a data point and tell whether or not this data point is can have adverse behavior to the model. The way that we do this, you know, at Robust Intelligence, basically we build frameworks for tests, and then we create hundreds of tests, and then these tests become these atomic units that we're putting together to create powerful tools for eliminating AI risk. So I've been told that I can't do this talk unless I'm going to have one slide that's going to have the AI development pipeline. So here's my slide about the AI development pipeline. I'm sure you've seen variants of this, you know, in other talks or kind of blog posts. So here's mine. And then I think kind of like in the AI development pipeline, you know, we start with developing a model. You know, we kind of develop the architecture, then we train the model, we deploy the model, we perform inference of the model, right? And then things happen over time, right? And we go back to like, you know, developing the model again, training again, and so on. So basically, all these different aspects in the development pipeline can be, you know, can be protected from risk in all these using kind of appropriately kind of designed tests, right, built as these systems. So you know, when we're developing a model from architecture to training, we perform model stress testing, right, to ensure that the model is, you know, to ensure that the model is mature to go into deployment. As the model is kind of like, we do stress testing of the model, we basically can perform deployment testing to see whether there's whether the model performs well on production data, not only training data. After we do that, we perform continuous testing on the models, right, as they're kind of running in production, and, you know, variables change. And last point is that in addition to all those, we put what we call an AI firewall, which is a classifier that tries to pick out bad data that's coming into the system and filters it out. Okay. And all of these are basically their tools, and all these tools are built using kind of hundreds of tests that we put together. So in this talk, I can't cover kind of the basics for all of them. So I thought I'll just start with the first part, which is model stress testing, right? So I'll focus. I'll just focus on that. Okay. So in order for me to talk about model stress testing, I want us to like understand what is the problem. Okay. And I think kind of to kind of best understand the problem, it'd be good to look at the results of an experiment that Harrison here in the company ran, testing kind of model robustness to bad input. Okay, so what was this experiment? In this experiment, we did this over various data sets. This table is going to be on one data set. It's a publicly available data set for the Titanic data set. And what we did is we took several kind of standard models, like off-the-shelf models from from standard libraries and frameworks. And we also used platforms like Data Robot and Google's platform for model development. So basically we have cloud platforms that serve these models, kind of like auto ML platforms. Okay, so we have a set of off-the-shelf models that we're using locally, and then we also have models that we're using in the cloud. And what we did is we wanted to test what is the robustness of these models to various kind of cases of bad input. Okay, so what are examples of bad input that we tested here? We played around with things like what happens if we change capitalization of a categorical like feature, right? What happens if we convert a number to a string, an integer to a float? What happens if we kind of create an integer overflow? What happens if we send a missing feature, like send a data point that's out of range, produce non-values, things like that. And when we ran this experiment, we kind of we ran it on kind of on a large number of data points, and we kind of ran it on these models, and these are the results that we got. Okay, all the ones that are kind of that we see here in green are places where the models perform perfectly well, and they were able to stop. They were able to kind of like call out a warning, or have kind of like wanted some kind of good outcome, right? Whenever this sort of kind of bad data was fed into it. Okay. And the areas they're in red are areas where kind of the models didn't know that bad input was fed into them. Okay. So I think this is a good time for me to pause for a second and ask people in the audience whether there is something that you notice when you look at this table.
I guess our live audience might struggle to respond. So is it the first and last rows that are, it seems like some of the rows are pretty bad all around.
The what, sorry?
Oh, I was just saying some of the rows in this table seem like they're zero everywhere, which
exactly, right. There's a lot of consensus, right? Which you can say, wow, that's kind of surprising that there's just like kind of so much consensus across, right, these, these different models, right? They almost kind of like together, almost they fail together and they succeed together at stopping bad input, right? And you kind of want to say, well, what is it about, about the way that we're building models, right, that, just sort of like, allows them to kind of like succeed on some and fail on others, right? And I think if we can understand that, right, then that's going to allow us to like focus our energy, right, on developing kind of tests, right, that will succeed in stopping bad data where models fail, right? So To better kind of like understand that, let's think about, like how do models process data, and in this case, tabular data, right? So we have a data point, right? And let's say that we have a neural network, if this is how you think about models, right? But what happens is that it's not that the neural network takes in the model, right? What happens is that there's a pre-processing step in between, right? And that pre-processing is responsible for various things, right? It's very simple software, right? That is responsible for, one thing is to map, right, different features into, right, embed them and map them into kind of like, numbers, right? So that they can be processed by the neural network, right? And as it's doing that, it's also giving us for free, right, some kind of like input validation, right? So it's like checking whether, like, if the number 36 is represented as a string, right, it can check, right, whether, whether it's actually a number, and then, kind of convert that to a number nicely. Or if there's like an integer overflow, right, it can kind of call a warning, right? The problem is that if you think about it, these pre-processing frameworks, right, they're very limited, right? Why are they limited? They're limited because they don't have context, right? If I now feed in a number of, instead of 36, 1985, right, the pre-processing software doesn't have context about the data, and it cannot make a decision whether 1985 is legitimate input, right? And as a result, right, I think kind of input validation, right, through pre-processing exposes models to bias and bad data and adversarial risk and poor model performance. And kind of one of the biggest things that we're seeing that in a lot of kind of organizations, right, there is a lot of reliance on pre-processing to perform this kind of input validation. And because there's reliance on pre-processing to perform this input validation, right, this is when they get hit pretty hard with like various aspects of AI risk. Right. So one of my takeaways is like, do something, but don't just rely on pre-processing, right, to perform your input validation, right? That will, that pretty much like embeds problems in your system that you and other people are going to have to firefight. Okay, so going back to this, if we look at like the places where models fail and where models don't, it's pretty consistent with what we just said, right? So if we look at capitalization, for example, right, pre-processing, of a data point does not have context about the data, right, to tell whether the data point should or should not be capitalized. If we look at like a data point that's out of range, right, with a single data point, pre-processing cannot tell whether 36 or 1985 is legitimate input, right? And that's where they fail. So what I want to talk about is how do we build, right, like kind of a system for stress testing a model, right, to basically ensure and call out like bad input, ensuring that bad input is not going to enter the system. So I'll give a quick like analog from cybersecurity. And I want to differentiate between two parts. In cybersecurity, we differentiate between vulnerabilities and malware. Vulnerabilities are basically instances that could hypothetically be exploited to harm a system, right? And the analog for, in machine learning is that basically these are synthetic data points that we can generate, right, that can cause model failures. And the important thing is that we measure the impact of these bad synthetic data points. The other aspect is malware, and again, in cybersecurity. And malware is not hypotheticals. This is now software that's actually harming the system. The analog for us in, I think in AI, right, is that this is data that's actually bad, that actually causes models to err, right? Not synthetically generated, but actually bad. And the important thing here is to be able to estimate the likelihood of bad data points in our data set. When you're performing stress testing, you want to like understand what's the severity, right, of a problem. And in order to estimate severity, you basically look at it as something like the impact times likelihood. How much can this how much can this issue impact the prediction of the model, right? And how likely is it to appear? So there's a lot to talk about for exposing both vulnerabilities and kind of malware. I think with the time that we have in this talk, I'll talk about how to expose vulnerabilities. I won't talk about malware, which we could do that for like another technical talk. That involves a lot of unsupervised kind of like learning models that detect, that know how to like kind of like effectively detect anomalies in data. Okay, so I want to be able to generate synthetic data points, right, that cause models to fail. That's what I want to do when I kind of want to create vulnerabilities. In order to do that, I need to understand why models fail. Okay, so let's just take a very, very simple example of a model that that is trained to either accept a loan or deny a loan. We have a data point, and when we feed a data point, right, it gets mapped right in the space, right, to some sort of high dimensional point, right? And in this case, I have like a very simple model. It's a like a linear model, and it's and the data point is either above or below the decision boundary. Okay. What happens is whenever we kind of have an error, kind of like what we saw with the 36 starting into 1985, then the model, basically the data points gets embedded like in a different place in the high dimensional space that all of a sudden falls in the category of where the model knows to deny it. So basically what we want to do is we want to do a vulnerability search, and that's to identify when and how a model can fail. So if we want to do stress testing, what we want to do is we want to use a given data point X in our data set to generate a different data point, a synthetic data point, X prime, right? So that like the difference between the prediction of the model, f of X and f of X prime is maximal. Okay. So we start with our data set. We create a model that's going to tell us whether to accept the loan or not to accept the loan. This is our data point. And basically what we want to do is we want to generate some sort of feasible region, right? D prime of X, right? That basically defines, right, what like kind of our search space, right? And now every data point in this D prime of X is legitimate. And now what I'm doing is I'm kind of performing a search, right, with a model to like identify, right, what is a bad data point that basically can hurt the model the most. That's what I do when I kind of expose vulnerabilities. Okay. So basically kind of this vulnerability search, it reduces to two things. It reduces to being able to transform realistic constraints into kind of polytopes, right? And the other part is now when we kind of translate them into these polytopes, then we're solving these hard optimization problems or trying to solve hard optimization problems over these polytopes. Okay, so what are these realistic constraints and polytopes? Basically, a lot of the art here is to kind of like, when we're defining these synthetic data points, we want to find out like kind of what are changes that are acceptable and what are changes that are not acceptable, right? Is changing a data point like kind of from like 36 to 1985, is that something that we think is acceptable in the data or not? So we need to define this sort of like feasible region, right? And as we define this feasible region, then we can kind of create a search through kind of optimization problems, right, that surfaces these vulnerabilities in a model. All right, so just kind of briefly, we talked about all these stages that we want to kind of protect through testing. So I'll start with kind of like this example of model stress testing. So we talked about how to develop this. What does this look like? Like, what does this actually look like? So what you can do is basically you can take a model, take a data set, you run it. And as you do that, you expose all the vulnerabilities of the data, and you get something that looks like this, right? So basically it issues out a bunch of warnings, right? And once it issues out a bunch of warnings, it just tells you we fed like this like garbage data point into this feature, right? And we expect the model to raise an exception. It did not raise an exception, right? And this is to test the model against unseen categoricals. Like how does the model handle unseen categoricals? So this is basically how you perform stress testing. You take the model, you take the data set, And then you basically kind of create this entire framework of stress testing, and then you stress test against all these different features, right, to sort of see whether the model, whether they can, whether there are vulnerabilities in the model, whether there's data that can be fed in, right, and have the models fail. For when you're taking a model from training to deployment, right, what you normally then do is you basically take your training set and you take your production set, and then what you do is you create tests to sort of see whether there are places where kind of the model performs well in the training set but does not perform well on the production set. And you can test for things like, again, unseen categoricals to see whether there are kind of unseen categoricals in the production set that were not seen in the training data set. And you can estimate, essentially you can also like estimate their impact through something like their impact and the severities through something like the stress test that we saw before. Similarly, you can do something like continuous testing. And with continuous testing, you can, what that means is you can basically continuously test the model, right, for kind of this, this bad input and how it kind of behaves differently from data that you've seen, like, in production or in testing. So the last part that I didn't talk about is like AI firewall. And this is all about sort of kind of how to stop bad data from entering the model. But basically, this is not much different from what we saw with stress testing. Once you've defined these sort of tests, you put a firewall in front of the model so that it can basically stop bad data from entering. Okay, so just to conclude, I want to thank everybody at Robust Intelligence. I think kind of we have the luxury of having really an amazing team of people that are working really, really hard to make this a reality. So I want to be thankful to them for helping me put these slides together, and also just sort of being my partners on this journey. We're of course hiring, so I'll just plug that in here if anybody's interested. Just to conclude, I'll just finish off with, I think, kind of what are the key points. I think the key points are that model vulnerabilities are basically, they're symptoms of AI risk. They're not disparate problems. And all of them can be mitigated through well-constructed tests. Model input validation, as we saw, is fundamentally limited, as it doesn't have context about data that doesn't have the data and cannot provide context to kind of what is reasonable. It's not reasonable. We're measuring severity in terms of like impact and likelihood of bad input, so it's important to like understand both impact and likelihood. And finally, I hope I was able to convince you that appropriately designed tests can generate powerful tools that can protect AI. And with that, I want to thank all of you. Thanks.
Thank you so much, Yaron, for your talk. Really, really interesting, and I think we have a lot of questions. I want to remind folks in the audience that please send in your questions in the live chat. We'll keep track of them and get them across to Yaron. So to kick things off, I guess I thought it would be interesting to, I guess, maybe ask the natural question. Like, there's some sort of analog between testing in machine learning and software engineering, right? Like, with respect to, let's say, unit tests or regression testing that folks do with software. And I'm wondering, like, in your talk, you talked about, I guess, in some sense, designing tests to understand what the AI model is doing. And I'm wondering if you have thought about how to reason about test coverage, which is, I think, pretty common in software, where you want to make sure that you're able to cover every line of code that is going to run in your program. And here, I guess it's less clear how to reason about that. Are you really hitting kind of all the different ways in which this model might fail? So I'm wondering if you've thought about this question, and if you have thoughts on how you could build tools to address that.
Yeah, I think that's a great question. So I think kind of if I understand correctly, then when we're talking about test coverage, is like there's so many things that can go wrong, right? Like, and we like, how can we make sure that like we're designing tests that that somehow like are kind of covered appropriately. So I think kind of sometimes like knowing what not to do is is the first step. So I think to me, kind of one of the things not to do is try not to sit in your office and hypothesize about like hundreds of different tests. Go spend 6 months building them, each one kind of like building each one of these individually, right? And come back and see kind of what the world thinks about it. So I think kind of we have accepted that, you know, whatever it is that we're going to do, like, is going to be is just going to be kind of like some sort of guess, and then you know, like, the world will inform us on what are the kind of the tests and what's the coverage. And I think basically, I think kind of the strongest tests that we have are not ones that we thought about, but these are ones where customers actually ask for them, and where kind of like you kind of interview them and you sort of say, okay, so is, you know, like, this problem is familiar to you, so like in what ways did you fail, and what are the and what ways do you think that you're going to fail, and whatnot. So I think kind of with that, you keep on hearing the same things, and you collect kind of a lot of kind of like the you know, and basically kind of you basically end up with a bunch of kind of like tests that are kind of like the important ones. The other aspect of it is building kind of a framework and an infrastructure that will allow you to basically build tests in like, you know, unless it's a really complicated one, in just a few hours, right? So if you sort of like think about things from a generalized perspective, right, and you have kind of that engineering culture, then when, you know, for example, like you know, a customer, doesn't matter which one, right, like says, oh, you know, but you know, I really kind of like, you know, this is a test that would be really useful for me, then literally kind of like in 2 hours, you can bake that into, you can create it, you know, with the right framework, right, and bake that into a production license. So I think kind of I think kind of, if I had to summarize it, listen to the customers and build a generic, principled engineering framework that will allow you to be agile and build these things quickly, and then kind of in a resilient way.
And I guess just to maybe push a little bit, like, would you say that there's kind of less hope in figuring out, you know, automated ways to understand test coverage? So for example, I think, you know, one common pitfall is that obviously humans can't think of everything, right? Like I can write down a few tests, but there's so much that I can't anticipate. And so, and that really gets to the heart of the test coverage issue, because that sometimes you don't know where the problem is, and it surprises you. Would you say like the right way to address that is to kind of be responsive by giving people the right tools so that they can kind of quickly write tests that cover that when they come up?
I think that's I think it depends on what I think kind of some of it depends on kind of what the task is, right? So for example, like stress testing is different from firewall. And I think that like what you're alluding to is, and this is very true, is that very quickly, right, you for some things, right, you know, you test and you write, like, you can basically put hundreds of tests out there and you can perform stress testing. But then there are other things where a machine learning model is, you know, is basically is the right tool, the right approach. And then, you know, testing can help us with maybe things like explainability. But yeah, but like for a lot of things where you know, for things like kind of blocking bad data, right? A very powerful tool is a statistical model, essentially.
Thanks so much for your response.
Hey, Yaron, one of the things I was kind of thinking about through your presentation was kind of once you have the test to identify these vulnerabilities, how do you go about kind of fixing them? Because, you know, one of the things that struck out to me about that table where like there was an entire row of reds, it seemed that, you know, certainly model choice isn't gonna fix this thing where like every single model has the same problem. So I'm wondering, do you have any thoughts or advice about on that front?
Yeah, so definitely. So for us, this is what we call the AI firewall. So like one of the things that, you know, if you'll ever like test our product, then you'll see that you can basically you run stress testing, it issues out all these warnings, and then you can immediately generate it immediately generates an AI firewall, which is like a piece of software that you can put in front of your model. And that piece of software is basically can block or flag bad data from coming in, right? So kind of like all these places where you're failing that you don't want to fail, right? Kind of from what we saw on the table, like all these reds, right? They're identified through stress testing, and then once they're identified, we automatically like take these tests, right, and convert these tests into firewall rules. So that's our approach, which we think is better than like retraining the model and putting a bunch of if statements and guardrails kind of in place.
Gotcha. We actually had a bit of a conversation in the live chat on YouTube from some viewers wondering about kind of adversarial attacks, especially in the image space. So we actually had a question from Phil Levis here at Stanford. Do you think it's possible to eliminate the risk of adversarial inputs? So I think potentially either the types of inputs that you're thinking about, or kind of the adversarial literature from the computer vision standpoint. Do you think it's possible to eliminate those without filtering also a bunch of good inputs? And Phil points out that security to the adversaries is typically modeled in terms of kind of resource requirements and things like that.
Yeah, no, I think that's a great question, and to me the answer is no, and but also I think that it's a very kind of well thought out question, because like I think as Phil is like alluding to, of course you can just like filter out everything and then you have like a very secure system, but also that system is not functional. So I think when it comes to like especially kind of like adversarial input, I don't think that we can really eliminate, right, the risk. So maybe I'm exaggerating a little bit when I say eliminating risk, but and I think that from I think kind of the principles I think are not different from from what we see in cybersecurity, right? Like we also don't expect to be able to kind of build fully secure like systems, right? And I think in the same way we will not be able to build secure machine learning model systems. So it will forever be kind of this arms race. And I think kind of the difference, obviously, from traditional cybersecurity is that the technical problems are just so different, right? But I think kind of from a philosophical perspective, I think it's exactly the same thing.
Well, yeah, that's a really interesting analogy to never being able to build a fully secure system. Yeah. Phil Levis sends a thumbs up.
I actually have a question that relates to the aspect that you touched upon in the first part of the presentation regarding potentially also having vulnerabilities with respect to multiple modalities. The example that you showed us with the table was mostly about tabular data, and also with the specific example of tabular data. I'm curious how you're thinking about like other modalities and also mixed modalities.
Yeah, that's a great question. So I think so with other modalities, like kind of the big ones I think we can think about are, right, they're of course like NLP, they're images. I think from our perspective, there is obviously there are cases where they're kind of mixed, right? There are kind of like there are features that are that are characters or things like that, and these things also show up in NLP. I think from so we have a system, we have an NLP system that's pretty soon going to be in production, and I think kind of my experience has been that the engineering principles are the same, right? The infrastructure is the same, the platform is the same, so like kind of all the foundations are the same. But at the end of the day, the actual tests are different, right? The actual tests are different. Like you need like a slightly different expertise and touch to like kind of understand, like the NLP systems, the NLP tasks, right? And so there's kind of like inevitably there's like there's a cost to like kind of introducing every new modality. But I think kind of if you're building your system in a way that basically, again, as we said kind of earlier, that knows at the end of the day to reduce like everything to like a test, and and even when you're talking about exposing vulnerabilities, if it has the right abstractions, then it becomes like very easy to kind of move around, not only create new tests, but also kind of like move around across different modalities.
That's very interesting. I mean, I agree. Like the whole structure can be exactly the same, but the tests themselves need to be different. Because, you know, when I was thinking about the constraints and polytopes that you were describing, I was thinking, well, if an image, you consider one pixel, one like a constraint or like a dimension of the polytope, then it becomes unfeasible, right? So there needs to be something different that works specifically.
Exactly. Because right, like kind of you define that polytope, and then once you define that polytope, then you send it to like, you know, as you kind of, you formalize it as an optimization problem, you solve it to the best of your ability, and you return it. So it's kind of about like kind of with these right abstractions and creating the right translation. Yeah.
Thank you very much for your answer.
Yaron, I wanted to, I guess, ask a question maybe, which is a little bit of a different tack. I'm curious about, you know, obviously, I guess in terms of companies out there that are thinking about these problems around, you know, measuring problems in your models and monitoring models. It's definitely a you know, popular area these days. There's a lot of companies out there. And one thing that I guess strikes me about the way you frame the problem is you talk a lot about security as opposed to, you know, doing poorly on real examples, let's say. I wonder how you think about, you know, kind of the distribution of the real world is kind of also pretty hard in some sense, right? Like without necessarily being adversarial. So I'm just wondering how you think about, you know, adversarial kind of examples and adversarial data coming into the system versus data that is real world, but is just very difficult for the system to handle, or do you not differentiate between them when you're thinking about testing within the system? It's possible, for example, that it seems like your system would work on both equally well, since there's kind of no distinction there from the perspective of how you design the test, but I'm just curious if you handle them differently in some way.
Yeah, no, for sure. So I think kind of the short answer is like, to us, like I think, and I think it goes back to what we said earlier in the talk. I think they're all one and the same. So for us, the journey has begun from, you know, security, like securing AI systems, and, you know, but you know, the question is securing from what, right? And for us, like initially, it was about adversarial input, and we basically we're working with organizations that care about that, you know, they're worried about adversarial input. Some of them are government agencies, and some of them are companies that care about payment fraud. They care about like kind of bot detection, like basically you know, areas where kind of, you know, adversaries are present and they have something to gain from fooling these models, right? And then for that, something that stress tests the system is something that's important. But we then kind of got into like, you know, I think it's I think maybe it was like I want to say a year ago, I don't know, where we got into like a lot of conversations with companies where like, okay, this is interesting, but my problem is not so much that I'm worried about adversaries. My problem is like kind of my adversaries are my own employees, right? They forget to put in a feature, they put in a feature wrong, or like kind of my customers are my adversaries, like they, you know, this or that, right? Or, you know, various aspects of it, right? And we saw that was kind of like a problem, you know, and yes, and you know, like, you know, distributional drift, you know, is this something that they care about, and where they need to retrain the model, and this is where we came up with continuous testing, right, and things like that. So I think kind of we found that like kind of all the frameworks and the principles were the same, whether you're worried about, you know, somebody that is using an emulator to like fool like a fraud detection system that's looking at like financial transactions, right? Or whether you're just, you know, looking at whether, you know, an organization of like 40 data scientists, right, is now kind of properly testing their models before they go into production, to making sure that, like, you know, the model knows how to handle a missing feature, you know, things like that, right? So those things, like from I think kind of from a company perspective and a business perspective, that has been, you know, like a pretty big change, because that basically opens up a lot more opportunities. But from I think kind of an engineering perspective, or you know, that hasn't been like such a big change.
Yeah, it sounds like you had an interesting kind of arc there with customers coming in and saying, like we have all these other issues with customers themselves, like giving us bad data. So that's pretty interesting.
And I would have thought that there would be some kind of different distinctions between what makes something adversarial versus like a user error or a development error. When I think of adversarial attacks, if you were to go to the example of like missing features or something, I would expect like certain combinations of tweaks to like multiple features. That would be some kind of sophisticated adversarial attack versus just messing up the date would be something closer to a user error. So it's really interesting that you can kind of take pretty much the same approach that you described to try to catch these things, whether or not they're like sophisticated and complex or something as simple as missing data.
Yeah, and I think that there's I think that there's a lot of kind of also like it's also been kind of like an entertaining psychological journey for me, right? Because you talk to people, and for example, there was a company where they're making kind of like very important decisions using these models, and all of a sudden, kind of capitalization completely breaks the model, right? But then you talk to like engineer number 73, and then they're like, well, like I don't care about that because the data is always capitalized. Country codes are always capitalized, right? Where, from where we're collecting them. But it's like, well, but maybe tomorrow they won't be. And maybe tomorrow you won't be here because you'll move to like a different team or a different organization or this or that. And nobody's going to remember it. And there's no kind of institutional memory, right, that knows, right, that country codes have to be like, that have to be capitalized, right? Otherwise, the model just is completely useless, right? And kind of identifying that is like, like not like the cost of that is just so big, right? So how can you not stress test your model for things like that? And you hear about like kind of like some parts like, oh, it's okay that my model doesn't doesn't handle that because there's pre-processing that somebody else wrote, and that's responsible for that. I'm not responsible for that, so I'm good. And it's kind of like similar story. But sometimes like but I think this is where we also looked at. We understood that an important thing is not only to kind of surface vulnerabilities, but also kind of identify what's their likelihood, right? So, okay, missing feature is catastrophe for your model. Okay, how likely is it, right? But then the nice thing is that you find a missing feature, or you find these things in the actual data, in actual, usually not in the training data because it's just so well curated, but in the production data, you find these things. And this is where you see kind of like a lot of customer delight, right? Where you surface the vulnerability, you're able to kind of like measure its impact, right, on the models, and then you're showing them that in production data they actually have instances of that, and that's been kind of like causing a lot of harm. So that's I think it's an interesting kind of like psychological, sociological kind of journey as well, as well as in kind of engineering business one.
Yeah, show people that something they didn't even know existed that was a problem, before it's even noticeable. That's awesome.
Yeah, I hope so.
It really sounds like when you describe that story of like engineer number 2 who says that it's okay because like the data has this property, it really sounds like something to do with like engineering practices and how you build a secure, stable, non-brittle system. I wonder if you have any thoughts about that. I think, at various points, we may have heard speakers give analogies to, like a civil engineer who's building a bridge would hopefully never say, oh, we don't have to like put the strut here because the mix in the concrete is going to be good enough that like our whole bridge won't fall down. I wonder if you have any thoughts kind of about that angle, like good engineering practices in the machine learning world.
I think it, well, I guess, like kind of, I think kind of, yes, like machine learning always aspires to kind of have, like we've been hearing a lot of kind of talks and discussion about like kind of trying to make machine learning rigorous and as an engineering discipline. And I think kind of people often give like civil engineering as an example. And I think that we're getting kind of closer and closer. Sometimes I'm not sure whether it's because like our bridges are falling apart and kind of like infrastructure in some parts of the country are just so bad, or is it that like machine learning is getting good? But either way, they're both coming kind of closer together. Yeah, I think kind of like, I think, you know, I think when we think, I think that the question to ask ourselves is like 5 years from now, 10 years from now, like, are we going to be developing like machine learning systems in the way that we have been so far? No, right? We're going to do this with like kind of all these tools and all these practices, right? That we're using in software engineering that we've kind of learned through. We've kind of like learned these lessons oftentimes like the hard way, right? And I think we're going to see all that in in machine learning, and we're going to see that like fairly quickly. When you think about the progress, when I look at the progress that sort of like machine learning has made as an engineering discipline, in the past, I want to say like 7-8 years, right? From basically, like coding some things in Python or C, right? They're very, very, very hacky, right? To kind of what we have today, it's phenomenal. So we're definitely on the right track. We're not there yet. And hopefully, like kind of part of, what we do is helping us get there.
Awesome. I also want to give you an opportunity, Yaron, to tell us a little bit about what's coming next with robust intelligence. What can we expect, in the next 2 to 5 years from you folks, and what should people watch out for tuning in?
The biggest thing is that in our last retreat, people asked me whether in our next retreat we can go to Barcelona, and I said yes. So that's, I think, the biggest thing for robust intelligence, like a trip to Barcelona.
Great.
Yeah, but I think kind of on a equally serious note, more, kind of like what we saw, we talked about stress testing, but like kind of there's kind of continuous testing and firewall. Like I hope that like I sort of the future that I see is more and more automation. And this is kind of like the things that I'm kind of one of the things I'm most excited about in the company is the AI firewall. So the idea that we're kind of like, that we're accepting the fact that we're automatically, right, making decisions about what data is fit or not fit to enter models, not only in trivial ways, but basically kind of like making some difficult decisions. So yeah, so that I'm like hyper excited about, and then we're going to see, I think, a lot of that soon.
Awesome. Thank you so much, Yaron, for joining us today, giving great talk, and yeah, it was pretty interesting to hear your take on what's happening in the industry around testing, and especially around machine learning engineering, I think, which is emerging as a pretty important discipline. I also want to thank the audience for tuning in today. Thanks for joining us, and go to our website, mlsys.stanford.edu, subscribe to our channel, get us to 5K subscribers, almost there. And next week, we're going to have Pete Warden talking about embedded machine learning systems. His talk is, I think, titled Machine Learning Everywhere. So that should be exciting. Thanks, everyone.
Thanks. Bye-bye.